University in Tsinghua and UC Santa Barbara. The speaker is Kaisheng, who is second year PhD student at Penn State. His advisors are Vijay and Yuan Chie, and his interests are energy harvesting and machine learning. Kaisheng?
Okay. Hello everyone, I'm Kaisheng Ma, a second-year PhD student from Pennsylvania State University. My topic today is architecture exploration for ambient energy harvesting non-volatile processes. This is a collaboration work between Penn State, Tsinghua, and University of California, Santa Barbara. And this work is sponsored by NSF a lot. So let's start with motivation and background. Wearable devices, Internet of Things, are trends of technology. So if I have only one wearable device like a photo glass, well, I think it's pretty good. I think it is still tolerable if I need to charge it once a day. But what if I have many wearable devices? Charging many devices every day can be a nightmare. So, but do we really need to charge them? Can they work without battery? I would say yes. Actually, there are already some real applications for energy harvesting devices. Here are some examples. The first one is RF-powered devices fixed on a dragonfly. The second, DARPA's project on solar energy harvester. Third, vibration. The last two are just medical applications using RF power sources. So, there are 4 common energy harvesting sources in our daily life. In this work, we actually designed 4 kinds of energy harvesters, including RF, thermal, solar, and vibration. With these energy harvesters, we get portraits showing this slide. So different energy sources have different characteristics. For example, the first one is PVRF. You can see it is unstable and it has very large variation. The max times the minimum maybe just several hundred times larger. The second is a plywood. Well, you can see it's a device fixed on my bike. I ride a bike, so I like this energy. It's kind of periodical power on and off. It has a pattern there. The third is thermal. The relatively scalable low. The last one is solar. Well, it relies too much on where you are, what is weather condition, and what is the energy orientation of the solar panel. So these kind of energy sources, they have one common thing. They are not stable. So what kind of impact the unstable power sources will cause to the current processor architecture? Well, here I provide one example. So the x direction is time, y direction is percentage of computational progress. For one cloud processor, for example, maybe PM P430, just to have some reset and do a little computation during the 4-part failure, and then reset again and again. But for non-volatile processor, we can just do continuous computing until we can get all the computation tasks done. So this kind of non-volatile processors is a good choice for unstable power. So this is our big one here. Energy harvesting demands architecture level redesign. So we are going to support do architecture level exploration to support tasks longer and for interruption granularity. And we are going to support delusional computers computing despite of power interruptions. And let's get on to architecture exploration. We start with a very simple no pipeline structure. And this is our exploration methodology. We develop an RTL level simulator, and we explore from a different complexity hierarchy from no pipeline, HPCA pipeline, and auto processor. And our target is a new optimized target, energy, and forward progress. So, what is our new target? The first, we call it the backup energy. Because energy consumption for backing up or restoring processor states, this represents the overhead of the system. The second, forward progress. The completed percentage for tasks running on processor depending on not only CPI, but also clock profiles, because we have clock failures. So how to make a processor from one cell to non-one cell? Here is no pipeline, no cell processor. I'll tell you step by step. First, we need to find what is important. We need to replace the data memory and the instruction memory with non-one parts. Second, we also notice that we need to back up PC and the register and put the essential data into my non-one memory block. To achieve this, we also need to design a non-one part controller to control the data paths and consistency. So, we propose several solutions based on the structure I just proposed. First solution, we call it backup change data every cycle, BEC. So for this solution, we do the backup in PC and most one register fire every cycle after my instruction. The second solution, we call it on-demand all backup solution. This solution, we just do the backup during call failures and backup all the things. The third solution, well, it's just to back up the change data, because during two call failure intervals, not all the things have changed. So just to back up the change the things. So this is our result. We care from two things, energy and forward progress. This is energy. So we'll first look at the backup energy. We can see that the backup every cycle solution is tiny. It's just a backup at most one register fire. Well, on-demand all backup and on-demand selected backup, well, they are a little bit higher, but on-demand selected backup is much better than on-demand all backup. Then for recovery energy, well, they are exactly the same. The reason is once the call failure occurs, sure, everything is gone. We need to restore everything. Well, the interesting thing is for energy pre-instruction, well, what if we have purchases with very high frequency call failure? In this case, backup every cycle solution is not too bad. For the low frequency, maybe I would say on-demand selected back solution is the best that we can choose. So, our conclusion is backup every cycle works better with extremely intermediate power sources like tens of kilohertz frequency vibration, while on-demand selected backup is relatively stable power sources. Okay, let's make it a little more complex. What about 5-stage backup? The first solution called non-conflict flow. This is straightforward, just back out all the latches, right? Just back out the latches during call failure. Well, I would say we have a better solution. I'm going to propose a shifted PC solution, just to back up one PC and re-exaggerate the mixed 4 instructions. So we have a little bit panicking on this. Let's see the result. The left one is the time panicking. So we can see we have 4 clock cycle time panicking, but I would say shifted PC solution is still better because we need smaller energy and time for the backing up, not only the recovery. If we see this right one, the energy panicking is more obvious. The shifted PC solution is much better. So backing up less provides more energy efficiency and forward progress. less is more. What if we have a very complex algorithm processor? We have too many choices. You can try to back out architecture, registrar, or physical, or both. You can try to back out ready table, map table, free list, whatever you want. You can recover everything. It seems too complex. So we propose 4 solutions for this algorithm. So the first solution, we call it minimum state resource backup solution, which means we just back up lots of uncommitted PC in the real buffer and flush all the things. And the architecture level registrar, because this is smaller than physical level registrar, and the map table. So we can try to back up more. The physical registrar just don't need to. And we can try to back up more with ready to move for list. We can try to have the minimum performance lossless solution, which is back up also a branch target buffer and a branch history table, which is performance related. So this is our result. The last one, we can see that it's just no surprising. We back up the more things, we need to pay more backup energy. Well, let's see the recovery. Surprisingly, the minimum level backup strategy provides the minimum energy requirement. So why? Because for the minimum resource policy, we need to do 2 things after recovery. The first, we need to rebuild like a free list, we need to rebuild like a map table, things like this. We need to cross cycles, we need energy. And we also need to re-execute the flushed all instructions in the real buffer. Well, how about the minimum performance loss? Just because we back up more, we need to recover more. This is simple and straightforward. So we have totally interesting problems for if we want to recover more things, we actually have less recovery energy. This is really interesting. We do designs always based on our worst cases. For example, if I have a threshold here, the P means the power has a failure. But this is not always the case. Because this is more ordinary. Even if the power is under the threshold, we still have some power income. But this kind of energy is wasted. Why don't we use this kind of energy to back up more things? So this is our flexible backup policy. We do 2 things in this policy. The first, we propose a sequence of priority. We need to say the PC in the real buffer is most important, and the second, architecture registrar. And then maybe stop operations in the low stop queue, and then one by one. So once we do this, we will back up the things according to the priority we just developed. So until there are no more energy available again. The second thing we do is we develop a atomic flag base. This means this base has only 2 states, successful or failed. We use this base to identify if this part has been successfully backed up to maintain the data consistency. So using partition wasted energy to back up more things for better performance, this is our thing. So we then build a model and validate it through a fabricated non-volatile processor. This is our validation methodology. We have our sources, we have my bench. Well, we have 2 routes. The first route is our simulator, RTL level based simulator. The second, we fabricate one case, THU1010N processor, and we compare performance and energy. So this is our result. This test bench, well, for stable sources, I would say extremely accurate. But for interrupted sources, we have max 4.6% error. This error from several aspects, like we need time to wait the oscillator to be stable. We need time to wait for the reset IC. We also, like each instruction, energy per instruction is also different. These kind of things we resolve for this kind of things. So this is our simulation results. Well, I would say one-clock processor is just matches previous intuitive feature. One-clock processor cannot finish tasks longer than 4 traces. The second thing is we observe the auto order is the best performance. This is really interesting. So why? Because auto order for low power is not the same as optimizing forward progress. And so forward progress and low power is totally different. And intuitively, auto order is considered for energy harvesting scenarios. But we propose that we can also have the choice in some cases. So this is our conclusion. We explore the space of non-volatile energy harvesting processors. We have a best architecture and policy during each design spaces, and we measure real system effects of failure, and our work helps to provide guidance for emerging wearable devices and Internet of Things. This is our video, and we have a demo outside in the Huawei's desktop tomorrow and now. Just have a visit. So you can see if we cover and find it in the panel, the system actually continues to work. Yep, it continues. So we successfully retained the states.
We have another measurement platform for max core frequency
and
our system can tolerate. We are so interested in that because it decides our max core failure frequency. And this is our non-volatile processor, and it's a facultative research purpose processor. And the test bench on it now is a counter, and the results of the counter are outputted through GPL3. Please note that we don't have a supercapacitor battery on this platform. And the input power of this testing platform is a square wave. And the positive square wave, which means we have enough power for the system, as we can see. And in this condition, our counter can work very normally. And the negative square wave means power outage, and our system doesn't work during this time. And as we can see that during power on time, our counter is working 38, 39, and under power failure condition is just FFP to pull up resistance. And once we have the power again, we will have a certain back. We define the system recovery time from the moment that the system power is on to the moment that the non-volatile processor can actually run. It's around 2.8 microsecond, and the backup time is around 6 microsecond. So this makes some power sources with really high frequency power failure can be used in this kind of system. And we are going to test another example with vibration power sources.
Okay, that's all. Thanks.
Questions?
Hi, what's your assumption about the power regulator circuit? The power regulator. What's the circuit between the energy harvesting and the processing?
Okay, it has several parts. Just the first front end is our energy harvester, and we have a DC converter. We have a very, very small capacitor, just nano farad. to store the energy for the backup and the recovery. And then we just put this kind of VDD to our system.
So why don't you want to have a supercapacitor?
Yes, this is a really good question. Well, because we have tested lots of things. Capacitor, ground-guided capacitor doesn't help to back up more things to have better power efficiency. Two things. The first, actually, even supercapacitor, we have leakage. And we have a supercapacitor design for a physics professor, especially for this system. But it doesn't work that well because there are two problems. The second question is when the voltage, you have two supercapacitors, right? You want to store energy. Once you extract the energy from the supercapacitor, the VDD will drop until the energy is half CV squared, the energy, right? So once the VDD drops under threshold, there are some amount of energy always stored in the supercapacitor, and you can never extract them out. These kind of things, with time passing by, they will be leakage. So